All right, mechanical translational elements. We're only going to get partway through this lecture. We're just going to get through springs, but we can get the intro and then through springs. So we now introduce a few lumped parameter elements for mechanical systems in translational, i.e. straight line motion. Newton's laws of motion can be applied, of course. Let a force F and a velocity V be input to a port in a mechanical translational element. Okay? Since for mechanical systems, the power into an element is the product of force and velocity, we can just say power is force times velocity. And we can call F and V the power flow variables because when you take the product of them, they give you power. So that's why we call them power flow variables. Some mechanical translational elements have two distinct locations between which its velocity is defined. For instance, the velocity across a spring's two ends would be two distinct locations where you can define a velocity. Okay, so for a spring, you would have two ends where each end has a different velocity, and you could talk about the velocity drop or the velocity difference between those two points. And other elements have just one. For example, a point mass, there's really only one velocity on the point mass. The velocity of which must have an inertial reference frame. So when we have that, where there's like a mass and there's only one velocity point, we are assuming that you mean the velocity relative to some inertial reference frame, because Newton's laws require an inertial reference frame, right? You may not have, this may not have occurred to you before, but a velocity is always a quantity that's relative to between 2 points. Okay, there's always a reference for a velocity. So if you don't believe me, then say you were, out in space and you looked at Earth, you'd be like, they're wanging around real fast. But when we're standing here, we don't experience that velocity. But velocity is relative, so you have to have a reference frame. And for Newton's laws to apply, you have to have an inertial reference frame, which means that either it's a constant velocity or it's zero velocity, because zero is constant, which is pretty sweet. Nice quality of zero that I like. Okay, so this is analogous, notice, to how a point in a circuit can be said to have a voltage, by which we mean a voltage relative to ground, right? We say a point's got 12 volts in a circuit, what we mean is 12 volts relative to ground. And when we say that a mass has a velocity of 5 meters per second, we mean a velocity of 5 meters per second relative to some reference. Okay? All right. Good. Also notice I'm already drawing these analogies between mechanical stuff and electronic stuff. So if velocity is analogous to voltage, what do you guys think that force is analogous to?
Current.
Current. That's right. Take the product of the current and the voltage, you get power. Take the product of the force and the velocity, you get power. So that's the analogy we're going to draw. And it's also nice because force is sort of like conducted through an element, right? If you think about, like, say we take the spring. If you guys ever done that analysis where like you cut the spring at any point, you would always have the force on the two ends that has to be conducted through. It's just like, I think you guys did this sort of analysis in statics maybe with different members. If you cut a member, then like anywhere you cut it in there, like the force had to be transmitted through it. And so the force is transmitted through each member, and then there's a velocity across each member. And that's the way that we think about this analogy. So for mechanical systems, we're working up to being able to think about them in a really similar way to the way we think about electronic systems. And this analogy is already starting to emerge. Okay. Work done on the system over time interval 0 to t is defined as the integral over that time interval of the power. And we use this integration variable tau because we're good calculus boys, right? I said that because like we're good Catholic boys is like the phrase, right? I don't really mean that we're boys, right? That's not what I meant. I was just trying to play off of a term. Okay. I feel like I could make that worse if I keep going, so I'm going to just stop. Just for the record, I didn't mean for that to sound sexist if it did. It wasn't intended that way. But I probably am sexist on accident. So my apologies. Okay. It's good to admit it, you know? It's good to just say, like, I don't intend to be, but I probably accidentally am, and I'm sorry for that. Okay. So, good. So therefore, the work done on a mechanical system is if you substitute in for the power, the force times the velocity, you've got it. Okay. The linear displacement x is going to just be the integral over from 0 to time t of the velocity plus the initial displacement. So the linear displacement x equation, does that look like something? It's one of your kinematic equations, right? From dynamics, right? Physics. Okay. Similarly, the linear momentum is the integral of the force plus an initial linear momentum. Maybe a little bit less familiar, but good to keep in mind. We now consider two elements that can store energy called energy storage elements. Then we're going to consider an element that can dissipate energy to a system's environment called an energy dissipative element. And finally, two elements that can supply power from outside a system called source elements. So we're only going to consider the spring today. That's as far as I made it this morning, and I don't like to have you guys on different things. Okay, translational springs. A translational spring is defined as an element for which the displacement x across it is a monotonic function of the force through it. So remember what monotonic means. It means either always increasing or always decreasing. Right? So that's what we define a translational spring to be. Notice that there are mechanical elements called springs, right? We can buy them. Compression springs, tension springs. They're pretty great elements, and they do show up a lot in mechanical designs. But I want to stress something here. We didn't define a spring in this sense to be a mechanical spring that you buy from a catalog, right? We defined it to be an element for which the displacement across it is a monotonic function of the force through it. So a lot of things can behave like this, not just things that are called springs. So we'll use this to model all kinds of things, including so if you might have like a really common problem is you need to do like sort of vibration isolation. So then maybe you've got like a manufacturing environment, there's a lot of motors running in it, there's a lot of vibrations in the floor, but maybe you have like a piece of equipment that's sensitive to that, or like maybe it's like an optical microscope, and you're trying to look at something, but it's just all moving. You can't. So you gotta isolate that vibration. You could model the rubber feet on a table leg as being springs because you can compress them, and then the force that they exert is increases as you compress it. So you could think of that as being a spring. Similarly, you could think of like a metal beam or other member that flexes. Might not be in the shape of a typical coiled spring, but it could behave in a spring-like way. So we model lots of things as springs that don't look like springs. Okay. A linear translational spring, so a linear, so emphasis on linear there, is a spring for which Hooke's law applies. That is, for which the force is proportional to this displacement across it, with constant of proportionality K called the spring constant. It's typically a function of the material properties and geometry of the element. So if it's like a coiled spring, there are like lots of equations that can tell you like from the geometry what it should be. But there are lots of things, and oftentimes what we do is we say, it's complicated geometry, it's complicated material properties, we're just going to measure it. So apply a known force, measure the displacement, and you got yourself a spring constant, right? You guys did that in physics class too, right? Probably with like actual springs. Because you guys like had like a meter stick and then like hung masses from the spring. I did that too. I was a student once.
Did you ever do the one where they have the vibrator and it vibrates a string? So
Yes, the different modes. That's really cool. I like that one a lot. I have to say, physics labs do a really good job of being cool.
Yeah.
Like,
and then you get to engineering, and it's like
engineering is like, it's like we forgot that cool was the thing,
It's like
and we
the
like made
side-
labs.
It's like the side project is the cool thing now.
That's right. We're like down to business. Physics is fun. Engineering is like, you guys get to work.
Physics tells
Like,
you
you
how
guys
the
get to
whole
work,
world
you can
works.
make it
and
so
you're like,
everybody else can
"Oh,
have
that's
fun."
how it works.
Okay.
That's how it works." And then you get to engineering. It's like this is how gear works. And like, cool.
You know what it is? In physics, like it, since it's not a profession, it's more oriented towards just like understanding and knowledge, which is really cool. I think engineering, one of the reasons why it's a little dry in content is that it's really oriented towards, I guess, professional responsibilities and like learning techniques, which like
Very
yeah, I mean I don't feel like we need to like rob it of the fun. Like we should rename this class to be like mechatronics is cool. I especially cracked when people call it megatronics, and I'm like, yeah, that's cool.
Everyone always says Megatron. I'm like, whatever. You're
You're
right.
like,
Yeah,
yay,
that's it.
Decepticons. Let's
Sounds like,
ride.
sounds like a cool band name.
Megatronics, yeah.
But if you were to build a Megatron, wouldn't it be in this class?
Totally. I mean,
Electronics and mechanics.
as if I haven't before. Yes, so spring constant, Hooke's law for linear springs. This is called the element's constitutive equation because, and I know it's surprising, it constitutes what it means to be a spring. That's why we call it the constitutive equation. I know. It's pretty engaging stuff. Okay. But like sexy diagrams though, right? I mean, like I spent some time on these. Look at how pretty that is. It's so pretty. I am proud of it. You can tell. Okay. Although there are many examples of nonlinear springs, we can often use a linear model for analysis in some operating regime. Like for instance, maybe those rubber feet on the thing, like maybe they act as a linear spring over like a little distance. But like if you went too far, it's not very linear. Like maybe maybe it'd start to act like F equals kx squared or something. Like that's possible.
If it goes on its yield point.
Well, it's still elastic. It'll still respond, but linear is an approximation that. So, like for a mechanical spring that you buy, those operate linearly over a pretty wide displacement. Eventually, they will yield, and it will be very nonlinear. But even before they yield, they'll be a little nonlinear. If you look at other types of materials that we model as springs, usually they become nonlinear real quick. But sometimes you only want to operate it in a linear regime. Like maybe you only want to operate it in like a small displacement window, which is fine. Like for small vibrations that are coming through, might behave exactly like a linear spring, or not exactly, because nothing's exact except exactitude. That didn't make any sense. Okay, so I just thought I would try it. So although there are many examples of nonlinear springs, we can often use a linear model. The elemental equation for a linear spring can be found by time differentiating the constitutive equation up here to obtain df dt equals k, and dx dt, we have a name for that. What do we call it? Velocity. And the reason we call this the elemental equation is that it relates the force and the velocity, which are our two power variables. Just as when we were doing electronic systems, we had an element that had an elemental equation. We called it the elemental equation because it related the current and the voltage.
I think I'm seeing inductors coming out.
Yeah, this is an inductor. Also, the symbol for schematics is eerily similar to the inductor, but like not on purpose. It's just that they both happen to be coils. But like that's like an accident of physics. It's like not even. I don't think there's any deep reason why that's true. It just is that way. Maybe there is a deep reason. If somebody figures out the deep reason, you get an A in this class. Okay, so.
Found it.
Okay, so this is the schematic that we use. Looks like a coil because spring, right? Force, we'll talk more about sign conventions later, but we often consider to be the force in a member. We tend to say tension is positive and compression is negative, just like statics did. So there's the force, and the velocity drop across it is v1 minus v2, and we just call it velocity drop v. It just sounds a lot like current going through an element and voltage across the element, right? It's just like we're setting it up already. Great. The spring stores energy as elastic potential energy, making it an energy storage element. So we've got our first energy storage element. The amount of energy it stores depends on the force it applies. For a linear spring, the energy is 1 over 2k f squared. You probably have seen it expressed as 1/2 kx squared, right? And it's true for linear springs that you can express it that way because f equals kx, and just plug it in and simplifies to that. But it's deceptive because it makes you think that the energy stored in it depends on the displacement across it. When in reality, it's the force. So if you think about it, you compress a spring like an inch, let's say. If it's a linear spring, you could say, okay, 1/2 kx squared, great. But say that spring was nonlinear and you had a different relationship there. It doesn't really depend on x fundamentally. It depends on what the force is that you've sort of bound up in the spring. What kind of force? So I guess before the spring has sprung, what's waiting there? It's the force that's waiting. The displacement is just an accident of what the characteristic of the spring is. So you can express it either way, it's fine, but this one's considered to be the fundamental relationship. And it's subtly important in the way we define energy storage in terms of which type of variable the energy is stored in. So we will come back to that. All right, I'll see you on Friday. Oh, there is homework this week. It's just like chapter 1 stuff.
Persistent memory.
Yeah.